Rajesh, I think you are on mute.
Good evening, everyone. I am back with my webinar series of Igniting Power Engineers. This is the 19th number webinar, and it is a very special, with a very special guest, respected Amandeep Singh ji, with a very important topic of failure investigation of transformer. In fact, every equipment in the substation has a vital role to play, and role of equipments like CT, PT, isolator, CVT cannot be underestimated. But out of these important equipment, the equipment of utmost importance is the transformer. In the present era, reliability and availability of power supply is very crucial. And it is worth to state here that the failure of transformer affects your availability and reliability of power supply to the great extent, as it is cumbersome job to bring back the failure transformer to its place after its failure. Transformer, in fact, is the heart of any system and needs proper condition monitoring and maintenance. And today I am very happy that Amandeep Singh ji is with me, and he will be sharing his experience of transformer. He's a transformer expert in the power grid. But I feel the success is neither magical or mysterious. It is basically outcome and the consequence of your hard work, habits, and blessings of your mentors. When I say blessings of mentor, I always start my webinar with thank to Almighty, my family, my parents, my wife, my son. My mentors include respected P.P. Vai sir, K.K. Murthy sir, K.K. Gupta ji, N.K. Mittal ji, P. Ramachandran sir, S. Pao sir, Hitesh Chauhan ji, and Dr. Kamal Bansal sir. When I talk about the good wishers, well wishers, and friends, the Saket Gupta, Arvind Tukral, Dr. Vikas, S.K. Batra, and Vishen that comes in that list. Last but not the least, the team working 24/7 day and night to make this webinar happen includes Gulab and Ramdhani. And now time to give a brief introduction about the presenter, Amandeep Singh ji. He joined Power Grid in 2006 in ET11 batch. He worked as ET in Maithon substation of ER2. Then he was posted at Abdullahpur as engineer in 2007 and worked there in operation and maintenance for 5 years. He got transferred to NLDC in 2011 and worked there till 2017. It's a matter of pride that he was a part of team that synchronized northern, eastern, western, and southern part of India and presented paper on the PMU analysis at SIGRIC, Canada. Then he was transferred to Corporate Center Asset Management in 2017, and presently he is looking after transformer and reactor at CCM. And again, he is a member of Working Committee A339, A258, and TC 122 and 123. Now, time to hand over this platform to Amandeep Singh ji. And I hope with your experience, the people will get benefit. And now, without much ado, the stage is yours, sir. Kindly start your presentation.
Thank you, Rajesh ji. Thank you for the wonderful introduction. And I would like to acknowledge the wonderful work that you are doing for igniting the power engineers. And I'm sure we watch your many videos and we really enjoy them, because sometimes it is about a very trivial topic, but it is very informative, and it is very good for somebody who is just starting off, and it is as much relevant to someone who is also experienced. And that is why I see a host, as a host, you have drawn upon such a wonderful audience. I see many known fellows in the participant list, and I'm sure many others will also join shortly. And I believe the recording of this webinar is also uploaded on the YouTube, so it would be available for future generations too.
Yes.
So my topic, I would just like to start my topic. So my friends, what you see on screen is something that none of the utilities or the manufacturer or any other person would like to see. A transformer which is on fire and this thing is certainly avoidable, and it is not at all desirable. Like Dr. Rajesh Arora also said in the introduction, all equipments are relevant, but the transformer is in fact the heart of the substation. It is the most costliest equipment which is installed, and you want to take care of it. You want to ensure that something like this does not happen, and you want to do it also because not only because it is capital intensive, but without a transformer, the entire transmission of the power from one generating station to end consumer will not be possible. So my topic is failure investigation in transformer, but Dr. Rajesh Arora said that this is a very detailed and in-depth topic. So I would only cover it as in from an approach point of view on how a utility should approach or how a user should approach the failure investigation of a transformer. So first of all, just an overview. When we talk about a transformer, transformer consists of a core and windings, then bushings, and radiator bank or cooling medium. These are the main components of a transformer. Of course, when we go into detail, there are many subcomponents, many accessories also, but these are the core components, we can say, which basically form or constitute a transformer. Now, when we talk about a transformer failure, what actually fails in a transformer? Transformer failure can be a winding failure, which can be due to external short circuit, dielectric stresses, abnormal aging. Then bushings can also fail. Bushings can fail due to high dielectric losses or partial discharges. Then leads, OLTC, tap leads, or mechanical damage. Then core due to earthing issue, multiple earthing, connection issues, or due to ingress of moisture, rusting can occur, which can cause damage to a core. So these are the major components which can fail in a transformer, which can contribute to the failure of a transformer. When we try to detail on component wise failure, so this data is based on the reliability survey of transformers. So the transformer reliability survey, it says that 1% failure rate occurs for a transformer across all utilities. So in power grid, we have got a very low failure rate. We have failure rate of around 0.32%. But overall, when you talk about all utilities worldwide, the failure rate is 1%. But when we look at the component-wise failure, so in a transformer, around 39% failures are due to bushings, 32% failures are due to winding failure, then 10% is due to OLTC, 12% is due to magnetic circuits. In power grid also, our failure rate is more or less on similar lines. So when we talk about frequency of a failure versus severity, I have tried to plot on what can be the frequency of failure. So electrical disturbances can occur many times, because when our system is connected and there are some operations, some lightning, some disturbances can occur. So these electrical disturbances are the most frequent, and these also cause the most damage to a transformer or a reactor. And when we comparatively see lightning issues, insulation issues, maintenance issues, these are less frequent and they cause relatively less damage to a transformer. And what the least issue which is faced is overloading or sabotage, because particularly in India, our transformers, if we talk about transmission sector, they are mostly N-1 compliant. So overload is not an issue which we have faced. Of course, in sub-transmission or distribution network, overloading is a relevant issue, but this frequency versus severity plot is only for a transmission sector point of view. So here we can see that overload and sabotage are causing the least number of failures and least damage, as in the magnitude of the losses, financial losses to the utility. Now, if we talk about in detail the transformer failure modes, so transformer failure modes can be due to electrically induced, like lightning and switching surges. Then it can be partial discharge, static electrification, mechanically induced damage, which means that there is some mechanical failure mode, which can be due to transportation improperly. If it has been transported, there have been some jerks which have the transformer has experienced, or during in service, if there are frequent short circuits in the downstream network, then also the transformer will experience short circuit forces, which would in turn cause damage to its winding, because windings will there will be electromagnetic forces generated and windings will also shift. So this is a mechanical failure mode. And then there is a thermal failure mode, thermal induced failure mode, which can be due to overloading or overheating. Overloading can be due to transformer facing loads more than its capacity for a short time or continuous period, like what we are seeing recently for the renewable generating stations, with the generating stations where the renewable energy is getting pooled. So overloading, particularly when the solar is at its peak, is oftenly observed. So nearly for 8 hours, it is loaded to near to its full capacity, and then afterwards it is coming down almost to nil load. So this type of temporary overloading or overloading for a short period can also cause failures. And then overheating can also be an issue. Overheating is slightly different from overloading. It is possible that the transformer design is improper or the cooling system is not proper. Then in those cases, or there may be some hotspots which get formed inside the transformer, which causes local hotspots and damage to the insulation. So these can in turn cause the thermal induced overheating, which ultimately would lead to the failure of the insulation and ultimately failure of the transformer. Now, when we talk about failure investigation, so first of all, if there is any tripping or any other incident, so how the transformer needs to be investigated. So first we need to look at the definition of the failure investigation as per various IEEE C57-125. It defines that steps to investigate the failure. But first of all, we need to realize what is failure analysis. So failure analysis means that a logical system which is used for examination of an item or its diagram to identify and analyze the probability, causes, and consequences of potential and real failures. So this is the theoretical definition of failure analysis. If we talk about it in a layman term, failure causes the circumstances. It needs to be determined. When there is failure, you need to know what has happened, why it has happened, and what you can do so that it should not happen, something similar should not happen in the future. So this is the entire intention of the failure investigation. Now, when to start the failure investigation? Failure investigation can get triggered from one of these two conditions. If a transformer has tripped, so at that point of time, failure investigation will start. Or if the transformer was in service but you have taken it under shutdown and the tests show a sudden deviation, it does not mean that the transformer was in service. It may have been out of service, but now you intend to take it in service, or it continues to be in service and you have observed some deviation in the DGA parameters. So these also can be a trigger for failure investigation. So any routine test which shows a sudden deviation or a transformer tripping can be a trigger point for the failure investigation. So how to analyze? What should be the sequence of analysis once something like this has happened? So this is a flow chart which is describing all these sequence of, what all should be done right from when it starts and how it should supposedly end. But let's go up through it one by one. First of all, whenever there is any tripping, you should gather all the data. How many protections have operated? Mostly, if we talk about transformers, we have got like electrical protections and mechanical body protections are there, like Buchholz and PRD is there, then differential and REF are there. So whenever something happens, the transformer trips, you should first of all check how many protections have actually operated. Did all those protections operate, or did only one of the protection operate? Many a times it is seen, like for example, that tripping is due to PRD operation, and there is no other protection which has operated. And when we go and check it, then it is maybe due to some moisture which has entered in the terminal box of the PRD, which has caused this tripping, or there are some small birds or small animals like squirrels which have caused the flag, the plunger for the PRD to operate, which has ultimately led to the trip signal. Then Buchholz also sometimes can get operated. It can get operated because nowadays we are providing NRV, non-return valve, in series with the Buchholz. So if this NRV gets wrongly actuated, it would prevent the flow of oil to and from the conservator, which and if the when the transformer cools down and the oil in the main tank is now cut off from the conservator tank, the transformer cannot breathe freely. So the transformer oil will contract, and due to contraction, the Buchholz air will get trapped, which can lead to Buchholz alarm and Buchholz trip also. Then maloperation of differential can be due to any fault which is outside our transformer. It can be a CT failure on, especially on the IV side, or jumper failure, or LA could have conducted. And REF protection is a specific protection which is taken from the bushing CTs directly. So in certain cases, we have also seen that REF protection operates because there is some issue in the CT circuit, or the cable has got damaged. So there is unbalanced current. And due to this unbalanced current, this REF protection has operated. So first of all, you have to rule out all these maloperations. There can be many more causes of the maloperations. So you have to build an initial database with yourself, where you have established what all are the causes of maloperation, and every time something operates, you need not get worried too much. If it is a maloperation, you need to simply identify it, cross check it, and then tick it off your list, so that your equipment availability is maintained. You should also consider the weather conditions. What are the weather conditions at the time of tripping? Was it raining, or was it some storm was going on, which could have caused any external element to come into picture? So the fault may lie external to our transformer, and you also need to correlate the data from your disturbance recorders, the sequence of events. A disturbance recorder will give you an idea if there has been a rise in current, then that means there is some fault in play. But if there is any tripping without any rise in fault current, or rise in even normal current, then you can suspect that the fault lies elsewhere. Now, once this stripping has done and you have done some initial investigation within your control room or at your remote operations station, then you need to correlate these factors with the actual condition at site. Somebody needs to go out and check if there is any foreign object around transformer. There have been incidences where some monkeys have come on the transformer, which have caused trippings, peacocks, birds, or some object have come flying from outside the station due to systemic conditions which have caused the tripping. So you need to rule out these foreign objects, and then you also need to identify whether there is any significant damage to the tank or the bushing prior to, if you have identified that this is a maloperation, but still whether there have been any other damage to our tank or bushing, you need to identify it. You need to see if there is any overheating. It is advisable if you do a thermovision scanning of the transformer just to see whether there is any hotspot getting formed, what is the oil level in the tank, whether PRD, if the PRD has operated, whether oil has actually been released or not. So these factors you need to check out, you need to verify so that you can gather some more data. Once you have done and you have ruled out all maloperations and you have identified that now there is some particular issue with this transformer, so now you need to take up the LV diagnostic testings. So LV diagnostic test will help to identify the weakness or the fault inside the transformer. An important thing to note is that there have been incidences where the LV diagnostic tests have been all healthy, but still the transformer is damaged, particularly if we see a failure towards the neutral end. So if there is any damage to the transformer or a reactor, and there have been some incidences when the damage is in the neutral side, because winding resistance and all other test parameters are healthy and still there is fault inside the. So a good LV diagnostic test does not mean that our transformer is healthy. If there is definitely some fault, you will need to go to the next step, which is the internal inspection. But this may give you an indication on what is the likely fault which lies inside your transformer, and it would give you some assistance in making the final decision. So all these LV test results are to be analyzed in totality to indicate what is the problem in the transformer. So what are the tests? So these are just some of the tests that we mostly carry out. The most important is the one at the last, dissolved gas analysis, then IR test, insulation resistance test, then other routine tests like turn ratio for a transformer. It is not relevant for a reactor. Then DC resistance, then oil test also. It can help you identify whether there is any issue with the moisture ingress in the transformer, but this should be relevant more during our routine maintenance too. And another test is SFRA test, frequency response analysis, which we mostly do, like I said, when we suspect a mechanical damage inside our transformer. So it is also very helpful in even indicating many minor disturbances inside our winding or bushing lead area also. So this is a small interpretation of the test result. So let us say if there is any turn-to-turn short within the winding, then oil test, turn ratio, winding resistance, exciting current, induced voltage, FRA. All of these tests will indicate some problems. If our winding is now open, so turn ratio and winding resistance will indicate some problem. If there is insulation damage, then insulation resistance, excitation current, FRA will indicate some problem. If the moisture levels are high, then the oil test results will also indicate some problem, and IR value will also deteriorate. If there is any mechanical damage inside, like I said, due to short circuit forces, then excitation current and induced voltage, and most importantly, our FRA test will be quite helpful in identifying this issue. And then if there is a core overheating, then IR, core to ground mode, and excitation current will indicate the problems. Now that you have got a brief idea on what is going to be the likely cause based on the LV test results, you need to confirm your hypothesis and you need to carry out the internal inspection. So oil evacuation needs to be done mostly in a 500 MVA transformer. There is around 100 kL of oil, and you need to have proper setup. Oil evacuation, filtration plant needs to be there, then tanks, and simultaneously as you are evacuating the oil, the dryer needs to be injected from the top. Though this dryer ensures that there is no exposure of the winding to the moisture, and the personnel who are going to enter the tank for the internal inspection, they are also safe because they are able to breathe properly. Because there have been some incidences where a person has gone in for internal inspection, and due to less oxygen content inside the tank, availability of less oxygen tank, and moreover also because, let us say, if there is any fault which has happened inside, and once you evacuate all oil, even then some gases, these fault gases may remain inside the tank, which can cause suffocation of the person who is entering. So that is why, because earlier we used to mostly use N2, dry N2, but now we have shifted to dry air to ensure that our personnel are safe when they enter the tank. And besides ensuring the safety of our personnel, we also need to ensure the safety of our transformer also, because we are going to inspect it. So a proper safety suit needs to be worn by the people who enter. So this will ensure that external dust, dirt, or other such things do not enter inside the transformer. So this safety suit will also ensure that our personnel are also they are also safe, and our equipment is also safe. So there is sort of a bubble formation between the two, even when they are inside. Then recently, based on our experiences, because our transformers are now getting more smaller due to more optimization of design, so there are many places inside the transformer, particularly around the winding, where a person cannot actually go and see what has actually happened. So a mobile camera with a boroscope would be helpful to use in such conditions. And at PowerGrid also, now we have procured these special boroscopes. So whenever there is some hard to reach place, we simply connect it to the mobile phone. And these are long 1 to 2 meter length optical fibers. And with that, we can see also what has happened at places which are slightly more challenging to get actually visual inspection. Then a collapsible ladder is also advisable, because at times you need to climb up and see the top portion of the core, or the other HV lead exits. So a collapsible ladder will be helpful in such a condition. And then a torch also is beneficial. So now that you are ready for doing an internal inspection, now it is the time for actual internal inspection. So what are the checks? So these are just a basic set of checks. You need to see, like for oil, you need to see what is the color of the oil, if there is any smell, if there is any free water inside, what is the debris inside, because many times when there are actual failures, you see a lot of carbon getting deposited. So where is that carbon located? What is the amount? What is the location? Because the first person to enter the transformer is going to be very critical. Once a number of people will enter, it is possible that this debris may shift here and there. So it is very important that the first person who enters does a video recording of what actually he finds, so that even if that person is not such an expert, even if some expert wants to see it later on, he can just verify what is the actual condition or what could have actually happened. Then if there is any sign of any carbon tracking, you need to identify the location of the tracking, the amount of tracking, the damage, the extent of damage. Because recently at one of the failures at one of our stations, we when we first entered that particular reactor, we first saw one spot of tracking. So that was the cold point of the tracking. So the flashover initiated from the corona shield, within the corona shield, so bushing base plate, and then later on we found two more spots. So there were three streamer arcs in that particular case. So it is very critical that you note down each and every starting point, ending point, so that you can hypothesize later on what is the nature of the failure. Then condition of the CTs, if there is any issues, many times CTs, some carbon spot or over voltages, transients that they occur, they can also be seen. So the condition of CTs also need to be taken into account. Then burns, discoloration and deposits on the tank wall, bushing terminal, corona shield, like I just said. And if there are any loose connection or splices, in some cases where transformer is feeding a lot of downstream faults, we have seen OLTC leads also getting loosed, the bushing leads getting loose due to improper fitting of corona shields. Then terminal boards can also get shifted due to frequent faults. So all these loose connections and burns, discoloration, then condition of the winding, whether winding has shifted compared to the other windings. So all these points also you need to record properly. And like I said earlier also, it is very important that the first person who enters, he is very much meticulously recording everything, so that it is beneficial for others also. Then OLTC compartment, if there is any unusual movement or any condition, stationary or movable contacts, then all that OLTC compartment also you need to verify. Then if there is any problem with the core, particularly any rusting is there, or you find some places the core is improperly moved. Recently there has been one incident where the core has basically the core earthing, the core lamination earthing was not proper. The insulation was degraded, so it was causing circulating current inside the core. So all these things need to be recorded properly. Now that you have established all the raw data which is been seen and which has been also tested through the LV test result, now you need to verify or establish the root cause. So while establishing the root cause, you need to also consider the history of the equipment. History of the equipment, not in as in this particular equipment, but also its sister units also, whether that particular design has had similar failures, if there have been some issues observed during testing, or it has come to light recently if there have been some issues. So all those factors also should be considered while hypothesizing or formulating any hypothesis of the cause of the failure. Then if there have been any unusual loading, extremely high loading, or cycles of high loading followed by rapid cooling, so those kind of things. And if there have been any unusual occurrences like system faults or lightning or frequent switching, so all these factors constitutes its operational history, which should be considered. Then should also consider the history of the equipment, as in the individual history of the equipment, the maintenance history, when, how frequently the maintenance is being done, and what were the earlier results of, let us say, if there has been a slow deterioration in oil parameters, which may indicate that moisture was slowly entering. So all this can be demonstrated by the maintenance history. And if there has been any recent modification and repair which has been done, which also could have caused or contributed to this failure, it should also be considered when you are establishing the root cause. Now, what can be the causes of insulation deterioration? Insulation can get deteriorated due to ingress of moisture. Moisture is the primary enemy of our paper insulation. Then contamination from any conducting particle. Let us say our core is getting overheated at some point, so core material may be getting due to this overheating, it may be getting disintegrated, and this will cause particles to escape out and enter into oil system, and these particles may get trapped somewhere in the winding, which can cause contamination of the winding. Then there can be thermal aging also. Thermal aging is nothing but hotspot formation. Hotspot formation, if it is improperly designed or if it is improperly cooled. Design is from engineering aspect. Cooling is may also be from a maintenance aspect, like if its pumps and fans are not running, so it can cause the oil temperature to go up, and when this oil temperature goes up, then the hotspot temperature, which are already very much close to our limits, so they may also go significantly higher. And in those cases we can see that the paper is getting rapidly aged, and it has been seen that for every 6 degree rise in temperature, the aging rate of the paper almost doubles. So you need to consider all these factors also. Then if there is any partial discharge or corona inside, partial discharge is a very up and coming topic, and we are also very, I mean, into this partial discharge, which I will be covering very briefly in our consequent slides also. Then if there is any mechanical damage or weakening from the vibration, it can also cause imbalance in the insulation, which can cause deterioration. So these insulation defect will cause the material defect and will ultimately lead to the failure of the winding of the transformer. But we need to identify what was the root cause of the insulation deterioration. So that is very much important. Then if we talk about the types of voltages which are seen in the windings, so in the windings normally the first is the low frequency or 50 hertz system operating voltages, which is the induced voltages on the transformer terminals. Then this induced voltages can also cause flow of current in the adjacent winding, and this is also of the same 50 hertz frequency. So this is the induced voltages in the adjacent winding. Then there can be abnormal low frequency system operating voltages. This can be due to overexcitation or any unbalance in loading, which can cause a low frequency flow of voltages. And the most dangerous of them all is the abnormal high frequency system voltages. These are the transient voltages, which are typically caused by lightning or resonance or switching. So this high frequency system voltage is very dangerous because it typically occurs for microsecond to nanoseconds. So due to this very short period of time, the actual stresses which is observed by the winding, which is dv by dt, so that is in fact very high, and it can cause sudden damage to our transformer. So these abnormal high frequency system voltages are most relevant, and mostly as per our experience also we have seen that they are something which get missed out from monitoring, and they are very much relevant, and almost all utilities need to uh, monitor them in a greater aspect. Once all of the faults are analyzed in the light of my earlier other observations, all data is gathered, all test results are established, internal inspection is carried out, then you need to form several hypotheses which need to be explained in a very scientific manner, where we based on our known physics, we should try to explain what could have caused the failure, what was the root cause, what it led to, and ultimately how we have ended up where we are. It is also once you form a hypothesis, it's also necessary that you should not stick to it. If there is some other data which comes to light which contradicts your theory, you should not stick to your theory and try to negate the other data. You should again start go back to the ground level and reform the entire theory. It is here very relevant if you do discussion with other peers. It may be from other sites, or it can be from other utilities, and whether they are seeing something similar. So this kind of platforms are already there. There are many platforms for knowledge sharing, and both official and unofficial. So at these platforms you can discuss what is the fault that you have observed, and based on the techno commercial factors you may decide to scrap your equipment and purchase a new one or repair. Here I would like to stress that recently Power Grid has started more focused approach towards site repair of our transformer reactor, because like Dr. Rajesh Arora also mentioned in his opening remark that if you talk about the period that the transformer spends to and from the factory and then at the factory itself, because there are many other priorities for the factory people, manufacturing of new transformers is priority for them. So time taken for a repair may also be even more than time taken for a new transformer to be manufactured. So based on these factors, recently Power Grid has started moving more towards site repair, where we have also accomplished some major things, and much more needs to be done. And for that, Power Grid is also moving forward. Now, when we talk about initiatives in Power Grid, like I said, the high frequency transients are very much relevant. To monitor these transients, we have captured, and because these transients cannot be accurately measured through a CVT, because CVT is attuned for maximum accuracy of measurement at 50 hertz. So we have got this transient monitoring systems which are monitoring the system transients directly from bushing. Bushing basically acts as a voltage divider, and from bushing test tab, when you monitor, you can see a lot of transients at very high frequency. Such equipment we have used, and it has been very helpful to us, and we have been able to monitor a lot of transients. But much more needs to be done, because we are still also learning about this such type of transient monitoring. So more work needs to be done, and if more data is available, then I'm sure that more things will come to light sooner. Then we have also developed RIP bushings up to 800 kV class. So as on date, Masa and Trench make RIP bushings are already in service, 800 kV. And then UHF based PD monitoring system we have also purchased. We have purchased 4 sets. So these are used for online monitoring, and then these are UHF based, and we are also going for acoustic based PD monitoring from a third party vendors. So acoustic based PD monitors we have not directly purchased. We have purchased only UHF 4 sets that are being used. So these are used wherever there is a transformer reactor, we suspect that there is some strong PDs inside. And another thing is that we have also experimented with alternative oil, transformer oil alternative, as in natural ester oil. So world's first 420 kV natural ester based reactor was charged in India at Maithan substation of ER2. We have also used GTL oil, gas to liquid oil, for our one reactor at Indravati. So all these new initiatives has helped us in bringing down our failure rate, because we have standardized the RIP bushing. So the failure due to bushing failure has been reduced. Now we have standardized RIP bushing from 400 kV up to 145 kV. Even for 52 kV, it is optional. So sometimes we are taking RIP bushing, sometimes we are taking OIP bushing as per the requirement. And regular oil DGA for OIP bushings, the older OIP bushing we are carrying out within the warranty period and even after the warranty period if there is any issue. So this ensures that the failure rate of any initial incipient fault in the bushing can be captured. Another method to capture this incipient fault is variable frequency tan delta. So here we have seen that if there is any moisture ingress in the bushing, OIP bushing particularly, then at lower frequency level, the tan delta values are higher comparatively. So this is how we have managed to bring down our failure rate. Like I said earlier also, world over it is agreed that the failure rate is 1%, and most leading utilities world over are having transformer failure rate of around 0.5%. But for power grid it is much lower than 0.5%. Our failure rate is around 0.32%. So this is a much better record, and this we have done due to these certain measures that we have introduced. Then failure attributed to windings. We have standardized FO sensor to detect the hotspots inside the transformer. Then online dryout system, online DGA were also used. So these were also have been helpful in cases where there is any incipient fault inside the winding. Then control switching device have been used in reactors and transformers, which prevents any high switching over voltages and inrush currents. So all these methods have helped us in reducing the failures which are attributable to winding. So with this, I conclude my presentation. I plan to conclude it earlier if Dr. Rajesh Aroda would excuse me, because but the topic is so much in depth. There is so much to say that I had
Sir,
to explain a lot.
sir, I would like to say it was wonderful, insightful, excellent, mind blowing, direct to the heart. And
Thank
we are thankful for this wonderful presentation from your side. Before I invite question from participant, I have very small 5-6 question I have noted down during your presentation. If you allow, I can ask.
Yes, sir. Yes, definitely.
Because that will cover almost the questions to be asked by participant. In the third slide, you have shown one slide, frequency versus the severity of cause. Okay. In
Yes.
that slide, you have mentioned in the X part frequency, that is in points. How did you get that slide from? Is it your power grid slide or you have taken from some international paper?
No, it is taken from international sources based on experience, and you would also notice that it is in $1 million. So
Dollar,
it
yeah.
is international experience. So what they have done is they have analyzed the data of many American utilities. So based on that, they have assessed, but the data that they have found, they have cross-checked with other utilities also, and it is more or less relevant. So this is because for transmission sector. So source is international, but it is still relevant.
Okay. And coming to the second part, you have mentioned that the thermal stress has two parts, overloading and overheating, very well defined. In overheating, you have mentioned the two parts, design and cooling. But what I feel, based on my experience, for transmission sector, it's okay. But when you go to the middle size voltage level, medium size voltage level, or distribution level, there is another source of heating, that is the harmonics.
Yes.
That is to be included.
Yes. Harmonics is getting more and more relevant in recently, because with increasing penetration of renewable energy, it is also observed in transmission sector also. But again, harmonics will cause losses, higher losses in core area, and they are of a higher frequency.
Right.
So they are not, the source is not for the low frequency or 50 hertz source, but they are on the higher side. So it is, I have covered those separately along with those transients.
Okay. Now coming to, you have mentioned about in the last slide, you are using the alternative oil, ester, natural ester oil, and
Yes.
that help you to bring down your failure rate. But I have one question, very simple question to make. When you are using ester natural air oil in your transformer reactor, how do you take care of the OLTC and that cooling settings for that one? Means when to start the fan, but because that the temperature is comparatively higher as compared to mineral oil. In that
Hmm.
case, then what should be the OTI and WTI setting?
Yes. This is a very relevant question. Fortunately, we did not have to deal with one aspect because this is a reactor, so it does not have any OLTC. Moreover, I would also like to inform that we are also going to purchase a 315 MVA synthetic ester based ICT also. But looking into the complicated issues related with the OLTC design for ester based reactor and the specific requirements for type testing, we have dropped that OLTC requirement for that ester based synthetic ester based transformer. So but in future someday we will have to go for OLTC based transformers, and ester in itself is a very big subject. Moreover, recently there was a conference in US which was exclusively based on ester zone
Okay.
itself, and even PowerGrid presented our paper on this experience of 420 kV reactor. So it was very well appreciated. So the experience mostly is that for up to, let us say, 66 kV equipment, if we go for any retrofilling, then there is absolutely no change you need to carry out. But for higher voltages, 132 kV, you need to verify whether the design is okay. But this is just a verification. There is mostly it is observed that the equipment is suitable for both mineral and esters. But 220 kV and above, you need to specifically design it. Presently, we have not deviated much from the established norms, whatever the OTI, WTIs are there. So we are sticking to the same limits, because one major benefit of the ester is that you can derive more thermal output out of it, because the esters have a much higher flash point and
Right.
fire point. So this benefit we are not directly capitalizing as of now, because what reactor we have purchased is designed for 50 MVR and operating for 50 MVR.
Okay.
We could have gone beyond, and in that case it would have been relevant if we want to allow it to go beyond its established OTI and WTI limits. So presently we are not using, but recently I was reviewing the one of the Italian synthetic ester based natural ester based transformer. It is designed for 250 MVA capacity, but it can go up to 150%, that is 375 MVA.
Okay.
So there they would be using those capabilities of esters. Presently we are using esters only because still India, we are, I would say, we are a developed country, but we are trying to implement all these latest things, and we need not to straight away jump
True.
to
Agree.
uh, just take a leap. We need to go step by step so that we are established and we are more confident. So that is why presently we have not deviated much as such.
Great. Great. Now coming to next very simple question. You have mentioned that you are using NRV in series with a Buchholz relay.
Exactly.
Yeah. Can you elaborate more how it will work in normal condition?
Okay. This is a NRV is a sort of a protecting device. Let us say if there is any fault inside the transformer and the transformer tank ruptures, and in that case oil inside the conservator, which would be around 5 to 10 kl on an average, would rush into this main tank, and this oil in the conservator would ultimately get wasted. So NRV works on a simple principle that whenever there is any sudden flow of oil to or from the conservator, it shuts off the supply.
Okay.
But if there is any slow flow, like when the
And in the
transformer
case of
is,
breathing, normal breathing, it is normal.
it is normal. It is for
Okay.
normal breathing or for normal operation. It is not getting cut off.
Okay.
It should not get cut off, but there have been incidences where it has wrongly operated, and like I said, which ultimately led to the operation of glucose. So it is a very sensitive device. Mostly around zero point 0.2 flow, more than 0.2, if there is any flow rate, then it would get cut off.
So in your session, in your slides, you have mentioned many times mole function. Now I am going to ask very relevant question based on your experience. If you have to give, you have to talk in terms of percentage of mole operation of transformer. What percentage that is so far your experience is concerned?
Okay, this is a very because maloperations do occur, and maloperations are acknowledged by all international forums. Even if you check out the cigarette documents, international experiences, maloperations, it is nowhere mentioned that maloperation do not occur. For our system, power grid system, even one maloperation is very much relevant, because reliability and I mean, reliability of the end customer may get hampered. So we are having a very rigorous uh, norm for trying to manage all these maloperations, and we have been quite successful also. We have made a lot of changes, modification in our technical specifications, especially for even small devices like PRD and calls. Like earlier, these equipment were not coming with any canopy, but we saw that many times due to entry
Yes,
of
of water.
moisture,
Yeah.
yes, water and moisture. So now we have mandated canopies.
Okay.
Then we have specified the material for gaskets so that there is no possibility of moisture ingress. And then if we talk about other factors also, even for terminal blocks, type of connection, standardization of the output dia of the PRD. So all these small steps we are continuously taking to try to bring our maloperation rate down. And there is a lot of scope in it still. And we also had close interaction with other leading utilities in India also, and abroad too, and what philosophies that they have implemented, and which have resulted in some help in further reducing those maloperation rates. So those aspects also we are going to implement, and we are already, like I said, we have the lowest failure rate. Maloperation is also
Right.
low, but whatever maloperation we have, still we want to reduce it further.
Last question. That question, I think everyone who has attended that webinar want to ask. How difficult is it as an engineer to take a call to recharge a transformer after tripping and bring back that transformer to the operation?
Yes, very very relevant question, Dr. Rajesh, and I tried to make it clear in my presentation also. Uh, Ultimately, a call has to be taken, because whenever there is an operation, you need to be absolutely sure that there is no issue inside the transformer. The issue was external to our transformer, number one. If it is not external, it is, let us say, a operation of a body protection, you need to rule out maloperation. I have found that many a times the gut feeling of the person who is taking this call gets developed, gets honed over time, and he is able to take a much more calculated decision, better decision based on his experience. But I am also sure that even a young engineer can also take a good decision. He simply needs to enlist what has actually happened, does not get panic at any stage, Like if there is any electrical protection operated, he needs to check whether there is fault current inside the DR. If it is there, that means that there is some fault. If there is no fault current, then that means there is no fault inside. And if there is any body protection operated, then he needs to cross check it with other factors. Like if only Buchholz has operated, whether Buchholz has operated due to some gas accumulation, or it is external, it is a cable fault. It can also be a simple cable fault also. So these factors, if even a young engineer, he writes it down, he crosses off all the other factors, I'm sure anyone can develop this kind of skill, and he can take a very good decision in a very timely manner.
Thank you. And I don't want to lose opportunity to call P. Ramachandran sir. He's here to give his feedback on the session. Kindly unmute, sir.
Dr. Arora, I have already put my comments. No, very informative and very interesting session. Thank you, Amandeep. Very interesting for all engineers.
Thank you, sir. Thank you. Thanks a
Thank you,
lot.
sir. Thank you. Now I would like to invite KK Murthy sir to give the feedback. Before I invite question from the participant. So kindly unmute.
No, I have unmuted.
Yes. Please.
First of all, congratulations to Mr. Amandeep for despite having very less service period, he has acquired a lot of knowledge on transformers. So a big clap to him. And further, I have got certain questions, no doubt. As you have said, LT testing. First of all, I would say 36% of transformers fail because of bushings is absolutely not correct. I would say I beg to differ on this. You see, I have written a paper which was published in international magazine, in which I had initially written 20%. So they asked me, you tell us the source. So ultimately, I had to scan for the source, and I got a SIGRE report which showed 17.6% bushing failure because of the transformer failure, because of the bushing failure. So like that, that is one question and one observation. The second observation is you have said that in the LT testing, you have not tested magnetic balance test and magnetizing current as well. That is also very relevant. I have written a paper on that, which was published in EMA journal, which was published in Electrical Mirror, in which we have found this whole magnetic balance and magnetizing current is okay. Only thing was bushing failure. So bushing was changed and transformers was put back in service in one case. And in another case, this LT testing, we could find out the transformers position with this magnetic balance and magnetizing current, 40 MVA, that was BHL transformer, which gave faulty, that R phase is faulty, which was finally when it was dismantled for repair, it was found, it confirmed that it was R phase. So now, so that magnetic balance magnetizing current is the initially, I would say, prima facie diagnostic test first. And next is NRV. You are saying where is the NRV position? Whether it is from Buchholz to this conservator, or I think it should be Buchholz to conservator, isn't it? In between Buchholz to conservator. And
yes, sir, it is between Buchholz and conservator.
And the next thing I would say, I would in that SIGRE colloquium also I had put that question. See, that was there in some Meridian Hotel also in 2019. In that I had given a this thing question. In synthetic ester, you say synthetic and natural ester, the flash point is too high. Agreed. Okay. So, but 360 degrees or 318, one is 318, the other is 350, 60 degrees. So, but the limitation of RIP is only 120 degrees. Okay. And that is of OIP is 105 degrees. And RIS is also 120 degrees. So what way it is going to affect? You cannot go further, you see. And as far as this winding temperature and oil temperature, you cannot say oil temperature. It is fluid temperature. You don't call it oil. You see, only synthetic oil is known as natural. Our mineral oil is known as mineral oil, whereas the ester fluid, it is known as the ester fluid. Okay, do you agree with me? So in that case, I have been searching for what would be the binding temperature and fluid temperature for setting the this body temperature issue. So ultimately, of course, I could get the answer from respected Lakhiani. So ultimately, I wrote. Even I wrote to Jhala, who had gone with you in Sigre, Paris session. He didn't reply to my question. So these are all my observations I would like to make. However, looking to your experience of, say, you joined, I think, in 2006 or 2006 in Power Grid, you have acquired enough knowledge. For that, I must congratulate you.
Thank you, sir. Thank you. All your points are well taken. Like I would just like briefly, very relevant RIV bushing 120, beyond 120, decuring issues, delamination issues observed. But I raised this question with the various manufacturers because recently they are setting shop in India also, and they have assured that it is a known issue, but their design aspect takes care of, especially for 120 degrees Celsius, and they ensure that sufficient cooling margin is there. Second, your test result, LB test result, definitely it was not an exhaustive list. It was only indicative list just to a beginner. And then bushing failure rate.
But then, excuse me, but then this is the basic prima facie test.
Yes, exactly. I agree.
Magnetic balance and magnetizing
Yes,
test. You see,
I agree,
we have been doing for 40 years for that. I've got
no doubt.
an experience of 40 years. Okay, and further, I would say, of course, I must congratulate Arora Saab. He has questioned so many things. You see, he is. I always appreciate him as a. I would say he is not only PhD in earthing system, but he is a versatile engineer. Congratulations, Arora Saab.
Thank you, sir. Now I would like to invite S.A. Pau sir to give feedback. Then I request participant to raise your hand if you have any question. I unmute one by one.
Thank you, Arora ji. Good evening once again.
Good evening.
I should congratulate you for your continuous effort in bringing the engineers together in this country on various aspects, not only safety and other things. Today's webinar, it's really a wonderful session. And Mr. Amandeep Singh, I should congratulate you for his nice delivery from start to the end. The transformer failures, his analysis, it's a vast experience. It seems, as Mr. Murthy said, during the short tenure, he acquired so much of skill that shows from his speech. So the failure analysis he explained are not only important to the substation engineers, it's for the manufacturer, it is for the maintenance engineers, everywhere. These tips can be covered, and it has to reach the engineers at large in our country. That's my wish. And another thing, the skill development in decision making is an important aspect. He touched upon it. It's an important aspect that in spite of so many gadgets, everything, again, we have to use our brain, and we have to be accustomed with so many things in decision making. He has rightly pointed out that point. Some sort of training to the persons. Instead of having so many gadgets, they should be given some training how to make decision making. Instead of whether rejecting merely rejecting a false operation or accepting what's the root cause, as he told out of his experience. Those things should be made transparent, and write-up should be disseminated among the engineers of this country. And one more thing I would like to appreciate on him is power grid, especially the power grid, for the low failure rate of transformers exceeding the international developed world. We should appreciate it. And I want to raise only one aspect. I want to get it clarified from you. The transient monitoring you told, sir, is it developed indigenously? Because most of the transformer failures are attributed to the lightning and surge traveling waves. If there is a transient monitoring available in-house, will it be bearable, affordable, or is it an indigenous, or we have to depend on it's a technology issue? It's an important aspect because it can be replicated in so many other areas also. We are losing lives in the country due to lightning and other things. A lot of substations, even 33 kV, 110 kV, and 230 kV substations are there. Is it possible for us to know more on this? Thank you. Thank you. Anyhow,
Sir, transient monitoring, earlier it was expertise of the foreign parties, but recently if you establish, we have seen that if you establish some confidence and you give opportunity to young or I would say Atmanirbhar India, so some domestic parties have also shown interest, who are ready, willing to develop such products for us. And if we give them opportunity, I'm sure they would be able to demonstrate. I see no reason why we should always be dependent on foreign sources for every solution.
Great.
Thank you, sir. Thank you.
Now I would request Davis sir, kindly unmute and start your question.
Yeah, good evening, Dr. Arora and Mr. Amandeep. I hope I am audible.
Yes, yes, please.
Okay, I missed the part of the session in the beginning, but in the later stage during the interaction, I was very much impressed with the answers and questions, and also Appos are also there, and so I have 2-3, not the questions, just to have insight from you. Point number 1, online monitoring of power transformers. One, and next is yes, transformer is one of the most critical equipment in a power system, particularly the power grid. One tripping of a transformer can pull down a city, and to restore it and then come out, so you will be under tremendous pressure. And we come across situation. I come with industry experience of 35 years, and yeah, I have come across many transformer failures. Now here, transformer bushing failure due to transient voltage, as Appos was mentioning about. So the lightning arrest is one of the protection, because anywhere in the transmission line, if there is lightning, yes, this is the weakest link comes to transformer bushing, if I am right. And with the latest technology for lightning arresters, how this can be managed? And if you have time permits, I would also like to hear something on the nitrogen-based firefighting system. I know it's a huge, big area what I'm asking with the shortest time available, but it's up to you to give a message from your expertise. Thank you. Thank you, Dr. Arora ji and Appos sir. And yeah, over to Amandeep.
Sir, this online monitoring system earlier, when we first started using 765 kV equipment, we had many experiments with many online monitoring tools. But slowly, as our experience developed and with the interaction with other leading utilities, what we have seen, and mostly in light of the recent developments internationally, if we talk about ISO 55000, towards which Power Grid is also committed to achieve,
Okay,
we have felt that all monitoring should be commensurate with the results which are expected out of it. So monitoring indiscriminately would also not be a techno commercially justifiable solution available. You need to identify even a small, like you said, that one transformer which tripping, which could cause failure of the grid for a critical city, or let us say a very critical installation infrastructure also. It would require more monitoring compared to a transformer which is uh, let us say even underloaded.
Right.
So it should always be commensurate to the actual, and this is the basic philosophy of asset management when we talk about risk evaluation, probability of failure evaluation, and how to get maximum return out of your equipment. So
Right.
that should be the leading concern of any utility, not only in India but worldwide. So it should always be taken in light of these factors, and this is the first topic. And then secondly, I've covered in detail that protection aspect, and NIFPS that you wanted to talk about, like you yourself said that it is a very big subject, NIFPS, and it is also slightly controversial at times, because there have been many voices that we have been hearing which speak for it, and there are also equally loud voices which speak against it. So
Okay, what is your experience of this operating this system effective? I mean, whether it is automatically take care of the firefighting, what is your experience? Because you have
in power grid, I would say, I won't, unfortunately or unfortunately, I don't know how to say it, but we have had no incident where there was any operation of NIFS which led to control of fire, because mostly what we have seen is that if there is any fault, there has not been any fire incident which has been seen, and the failure rate of these equipment, because mostly we are using it in northeastern region where there are lower rating transformer, but the failure there is even lesser. And for if we talk about other stations where we have been constrained to use NIFPS, there also there has been no failure. So fortunately or unfortunately, like I said, there has been no experience as such for NIFPS, but there are utilities for it. There have been demonstrated, even if you would refer, there is a special technical brochure also, 537 Secret technical brochure, which deals with the guide for transformer fire safety practices, which goes into detail on the ruptured disk and all such technologies, which should be more relevant. But for us, there has been no such experience where we have seen, let us say, a good operation or a bad operation.
Okay. Just to add to this, what I just one more minute, if it's allowed. One of the incident investigation I come across, there were 300 MVA transformers have failed, and the reason was one got fire because of the 220 kV indoor termination got blasted, and then transformer got fire, and NFPS which was there did not act. And that fire, now you can imagine a 300 MVA transformer, there is a 220 kV by 132 kV. Now you can imagine the oil which is burning, and that transferred to the next transformer because that firewall provided was not meeting the height requirements. Then the second transformer got fire, and then that transferred to the third transformer. Now you can imagine 300 MVA transformers, how many kiloliters of oil burned for almost 8 hours. Firefighters have come, and then they just watched over there and then trying to isolate the area from the other location. But it was extensive damage. 3 transformers have gone, and also the inside building, there were a lot of damages because of that wall which was provided for brick wall, which was not sustainable to the heat. So that's my experience.
More than the damage to the transformer, in such cases, we have seen the damage to the cables also, because all the CT cables and all equipment cables would have to be relayed, which takes even more time, and then end-to-end termination. So to account for that, we have at places experimented with process-based system, wherein all the CT connection, because and all protection connection come up to MD of that transformer, and then From there, optical fiber is laid. So in such cases, if you require a very quick restoration, then only one optical fiber cable through which all the signals are getting transmitted inside the control room. Only replacement of one optical fiber cable is required instead of laying entire CT cables to and from the control room.
Right.
Now I would like to invite Sharad Parmarji, kindly unmute and ask your question. We are already getting late.
Okay, sir. As far as sir has asked regarding the DGA of the bushing, so yeah, if we are taking the DGA sample, so is there any experience? Some of the result found low or whatever fail, and then we can change the bushing.
Good question.
Yes, very relevant, and I tried to cover in my presentation also. And again, this is a very big subject. We have had many experiences. I remember in Cigarette 2018 session, PowerGrid presented a paper on our experience for bushings. And what I would, if I would only briefly touch upon bushings, if we want to monitor, just looking at the bushing tan delta on a lower frequency level compared to 50 hertz, let us say 17 hertz, if you cannot go even lower. So if we see a deviation of more than 0.1% from the 50 hertz value, we strongly suspect that the bushing is having some issues, some problem. And in those cases, especially when we have done the DGA sampling through the top of the bushing, and we have found that hydrogen values were as high as 30,000 ppm. So the limit for hydrogen for a bushing is only 200 ppm. So when you say that hydrogen is 30,000 ppm, that means that bushing was as good as a bomb. So anytime it could have failed and could have led to the failure of our other bushings and transformer catching fire. So this kind of a situation can be avoided by just routine monitoring. We, based on our maintenance practices monitoring, we also identified certain make of bushings which are having higher failure rate, just which could have caused that higher failure rate for bushings, because that was a certain period and certain make which was having issues. So this kind of, that is why I said talked about peer discussion. If you talk about such things at such platforms, then you gain knowledge that certain manufacturer, some batch is having some issues. So you can also go back and you can analyze whether such similar equipment are in service in your system also, and you can take preemptive action.
Sir Praveen Gargji, kindly unmute and ask your question. You are waiting for a long time.
Mr. Amandeep, I am having two questions. One regarding Easter oil. There are a number of suppliers available in India, and both are natural ester oil and synthetic ester oil. Which ester oil is better for transformer? What is your experience?
Ester oil, there are two types of ester oils, natural ester and synthetic ester oil. And both have their own advantages, disadvantages. But when we talk about utilities in general, there are some issues with natural esters, like oxidation stability remains an issue. For synthetic esters, there are some other issues like processing, and ultimately cost always remains an issue, which is higher for synthetic ester. But many utilities worldwide, they have adopted synthetic ester, what we have observed, especially for higher voltage equipment. In fact, even in India, PowerGrid has used this natural ester, and we have consciously decided that we would not go with only natural ester. We will experiment with both natural and synthetic. Unfortunately, our synthetic ester based transformer got delayed, but soon it should get ready and should be commissioned in our system. So our experience presently with natural ester has been satisfactory. There has been no issue observed presently, but of course it is very short period because it has only been in service for last 1 year. It was commissioned last year in August, so it has just completed 1 year of service. And slowly, if there is some issues, because some utilities have reported that for natural ester, gel formation has been observed over a longer period of time at continuous high temperature, especially when there is some moisture in grass. So we are keeping our eyes open for that factor. And once we have more information, then we would be able to give you a better guidance. But presently, we have no reservation for or against any of these.
And now I have come to the last question of my session. Ullas sir, kindly unmute and please ask.
Yeah. Can you, hello, am I audible?
Yes, you
Yes.
are audible, sir.
Okay, okay. It is just not a question, it's sort of, you can say, suggestion. See, I'm basically electrical consultant, energy and safety auditor.
Okay.
So whenever there any transformer problems takes place, it leads to basically fire and explosion. These are the two hazards. So instead of leading this hazard, you can save it by installing this fast depressurization systems, which have been recommended in NFPA code 850, etc. So why don't you go for this fast depressurization system so that there won't be any fire? Because other means NISS and all what you have specified, it comes after the fire. It is basically firefighting thing, like they say high pressure water spray system and all these things. This is fire fighting system, but we are talking about fire prevention by installing fast depressurization system. So I have came across this such system. There's one company, a France company by name Sergi, and they have been installing these depressurization systems, and they are quite effective because those fast depressurization systems have been installed, and they have carried out almost 62 live tests on the transformers. So if you use these systems, I think failure rates will come down, and fire and explosion will also reduce drastically.
Yes. Okay. Like I said, our failure rate is already at a very low level compared to what other utilities have. Number one. Number two, if we talk about Sergi, we interacted with them in the past also. It was around 4 to 5 years back. There were talks of some pilot, but things didn't materialize because of some issues during the testing phase. Moreover, if you just check out SIGRE Technical Brochure 537, the Guide for Transformer Fire Safety Practices, it recommends that higher rupture disk, providing higher rupture disk will definitely allow for a better safety of the transformer tank, but it also comes with its own associated risk of maloperation of a rupture disk, which would lead to unnecessary outage or exposure of our transformer. Number one. Number two, it would also get associated because the more rupture disk you introduce, then more safety factors you are achieving, no doubt, but still there is more vulnerability in the tank of the transformer. So we already have PRDs installed. Typically, for every 25 kL of oil, one PRD is installed in our transformer. At least 2 PRDs are provided in each transformer or reactor, no matter how less the oil is there. So it should technically be able to release all the pressure which is getting generated inside the transformer whenever such thing happen. So that is why we have consciously decided to refrain from using rupture disks. So these are the factors which have come into pictures.
Sir, with that, I will say thank you, Amandeep ji. Thank you once again for a wonderful, insightful, excellent, and mind-blowing session. Thank you for sparing your valuable time. Thank you, sir. Thank you, everyone.
Thank you.
Thank you, everyone. Thank you.
Thank you, sir.